Welcome to the Omniverse Create tutorial on Physics Basics. This tutorial is for the 2020 open beta version of Omniverse Create. In this tutorial, I will show you how to build and simulate this buggy. You can see that the buggy can roll around and has a working suspension. We are going to be building it from scratch with a focus on physics properties. For starters, I loaded a scene containing just the individual blocks. These were exported from a third-party modeling application in USD format. They are only a list of about 150 meshes with materials for rendering and don't have any physics at all yet. They also need to be assembled. One can see they have no physics by selecting any one and inspecting the Properties window, which clearly only contains the basic mesh information but no collision or physics properties. Of course, when we press play, nothing happens. We also added a stage with a beach and palm trees, just so we have some sort of attractive backdrop while we work. Also, the beach provides a ground for the physics objects to settle on. We will look into this later. Before we start, let's quickly make sure the camera movement speed in the viewport options is set to be comfortable, otherwise moving around the scene will feel clunky and frustrating when we right mouse drag or fly around with WASD. I will quickly show you how it is possible to assemble compound objects from parts before we dive into physics. For this, we will put together a single wheel. Before we start, I would like to demonstrate a very important USD feature called layers. Layers are useful for a lot of different workflows, including non-destructive edits. Say the file we have open is being used for various other important purposes and we should not change it. However, if someone does change it, say by changing some meshes or adding more objects, we want those changes to be reflected in our scene. The solution is to add a new layer to the layer stack, which will have our edits. The new layer and the layer stack are both stored in different files, and our original file is not modified at all. Let's first create a new layer called buggyassemblylayer.usd on top of this scene. Next, we save the entire layer stack as mybuggytutorial.usd. We make sure we have the assembly layer selected before we start to assemble our first level. In USD, one should not parent meshes under other meshes, so we create a top-level frame called Xform. We rename this Xform to Wheel for easy reference. We drag and drop parent the meshes that we will use to compose the wheel under this frame. Our wheel will be made of an outside tire, an inside tire, a wheel hub, an axle, and a small spacer. When we select a mesh, it is highlighted and transformation handles appear. Instead of using the handles to move the parts, we will use text entry to exactly center it in the wheel frame. This way, we can make sure every part is positioned perfectly on the wheel axis. Now, when we select the top-level transformation, we can move and pose the entire wheel assembly together. We will also move all of the remaining meshes into a spare frame, just so we can collapse it and have less clutter in our stage. This wheel, however, still doesn't have any physics behavior, so when we press play, still nothing happens. Let's create yet another layer called buggyPhysicsLayer.usd, where we will now add physics. This will let us reuse our wheel assembly in scenes that don't need any physics with zero overhead just by omitting the physics layer. Before we do any simulation, it is very important to make sure the mass, distance, and time units of the stage are set correctly, because they have a very important effect on how units are interpreted, and as a result, how our physics will feel. In our case, they can determine if the buggy is to feel like a life-size car or a small toy. A wheel radius in our scene is just a few units, which at toy scale should be around a few centimeters, so we set our scale to be centimeters, kilograms, and seconds. When these are wrong, physics behavior can appear too fast or too slow. They can be accessed in the properties of the top level layer. Any stage that needs physics simulation must contain a physics scene, so for starters we must create one. The scene is a container for various global simulation settings like gravity. Next, we need to request some physics behavior for our wheel, which has two aspects. It needs a rigid body component that will make its transform be controlled by physics, such that it falls under gravity and can be pushed by other things. And it needs at least one collider component that will let physics know about the shape of the object. Both of these are automatically set up when we set it as a rigid body. If we look, we can see that the frame we selected now has a rigid body rollout, and all of the submeshes have collider rollouts. We can visualize the colliders by using the viewport eye menu and selecting to show colliders. If we press play now, the wheel will fall, but it will not collide with anything. This is because so far the sandy beach mesh doesn't have any collider, so there's nothing to collide with. Let's stop the simulation, select the beach mesh, and set it as a collider. Note how we don't set it as a rigid body, because that would mean that it would also start falling. We rather want to make it be a static collider, which is what happens when there is no rigid body parent, only a collider. If we simulate, the wheel will fall onto the sand below. Note, however, that if we try to roll it by shift left mouse dragging it, it doesn't roll very smoothly. Let's fix this. In general, the default behavior of a set rigid body is convenient, but often we want to do some fine-tuning. Here, the tires were approximated by default using convex meshes, which have flat sides and they don't roll very well. We can select the outside tire and change its collision approximation to sphere. This will roll great. Unfortunately, this doesn't fit the shape of the wheel very well, and the wheel will also roll in ways we don't want it to roll. In the future, we hope to add cylinder primitives in order to address this problem. For now, spheres will do just fine. Note also that, by default, colliders were added to some of the inside shapes that can never collide with anything, since they are entirely embedded in the sphere. Let's remove the collider components from these by clicking the X of the collider rollout. We only leave colliders on the wheel and the axle. We can now simulate and check that we get decent rolling behavior. This is a good time to look at the physics debug window. It has additional visualization options for when things don't go according to plan, and we see some odd behavior. In this case, especially the contact point visualization can be very practical. We are getting contacts as expected. I won't waste your time by assembling the entire buggy from parts in this manner. Instead, we have again exported an already assembled buggy USD from a third-party tool, and added rigid body and collider markup to all of the parts using the method we just learned. Let's load that file and continue from there in the next video.